Now that we have reviewed our boundary conditions, let's try solving for some reactions. Before we dive in here, note how we have defined our positive directions. Positive x is to the right, positive y is up, and positive moment about the z-axis is in the counterclockwise direction. So let's start with this first example in the top left. Here we have a member supported by a pin on the left and a roller on the right. And we have placed a point load at mid-span. This member here could be a girder with a beam framed into it where we are getting our point load from, and these supports could be columns on either side. So now let's solve for our reactions in terms of our point load. And we do so with our three equilibrium equations. First, we have sum of forces in the x equals 0. And in this example, and indeed as we'll see all of our examples here, we only have one force in the x direction, our reaction at the pin. There is no applied force in the horizontal direction. And so, as this is the only force in the horizontal direction, and the sum of all forces we know is equal to 0, this force must be equal to 0. Now let's sum forces in the y direction. Here we have our reaction in the y direction at our first support, and our reaction in the y direction at our second support, both in the positive y direction. Next we have our point load in the negative y direction, and this is equal to 0. Now we adjust with some slight algebra. ry1 plus ry2 is equal to our point load P. And that's as far as we can get with this equation. So let's jump to our third equation, our moment equation. Sum of moment about the z-axis. And recall that we can take this sum of moments at any location along this member. So let's take it at this point here. So now our sum of moments will be P times its perpendicular distance to the point, L over 2. And this point load will cause a rotation in this direction about that point, which is the clockwise direction. And so this moment will be negative. Next we have ry2 times its perpendicular distance, the total length L, and ry2 is creating a moment in the counterclockwise direction, and so it will be positive, is equal to 0. Again, we apply algebra. ry2 L is equal to P L over 2. Divide by L on both sides, and we get ry2 is equal to P over 2. Now we take this equation and plug it back into our sum of y equation, and we get ry1 plus p2 is equal to p, and so that means that ry1 will also be equal to p over 2. And so both of these reactions are equal to p over 2. Next, let's try an example where we also have a point load, but this time that point load is located a distance a from the support on the left and a distance b from the support on the right. And note that L is equal to a plus b. Similar to our last example, we will have sum of forces in the y is equal to ry1 plus ry2 minus p is equal to 0. And so we will have ry1 plus ry2 is equal to p. Next, with our sum of moment in the z direction, We will take the moment at the same location as our last example, at our pin support on the left. We will now have P times A, and again that will be negative, plus RY2 times L equal to 0. And here we apply simple algebra. Ry2 times L is equal to P times A, and we get that Ry2 is equal to P times A over L. As before, we plug this equation into here, and we get Ry1 plus P times A over L equal to P. And we can arrange that so that Ry1 is equal to P minus P times A over L. And we can take this further with a few more algebraic steps. If we say that P times 1 minus A over L, so simply extracting the common factor here of P. And now we can also say that this expression is equal to P times, in parentheses, L over L, which is of course equal to 1, minus A over L, close the parentheses. And now this is equal to P times parentheses L minus A over L. And now recall that L is equal to A minus B. And so we can plug that back in, and we get A plus B minus A over L. So finally, gotta keep scrolling to the right here, we have P times B over L is equal to our Ry1. And our Ry2 was P times A over L here. So this is P times B over L, and this is P times A over L. And hopefully when you first looked at this, you set up the expectation that the support on the left here would be larger than the support on the right, because our applied force is closer to our support on the left. And so we can quickly check our equations based on that expectation. We have P times the greater distance B over L for our reaction 1, and we have P times the shorter distance A over L for our reaction 2. And so, yes, we meet that expectation. Our reaction on the left will be larger than our reaction on the right. Now let's continue to a distributed load. And the units for our distributed load will typically be in kips per foot. And the way that we will solve for our reactions in this case is we will first find an equivalent point load at the centroid of this distributed load. And so our equivalent point load will be equal to, since this is a uniform load, W times L. And now you can see that this setup is exactly the same as our first diagram up here. And so we can base all of our equations off of what we have found already. So Ry2 will be equal to P over 2, or WL over 2, and Ry1 will be equal to P over 2, or again, WL over 2. WL over 2, WL over 2. Next we have a distributed load, but this one is not uniform. It is a triangular distributed load. As in the previous problem, we will find an equivalent point load at the centroid of the shape of this distributed load. And in the case of a triangle, that centroid occurs at 2/3 L, or on this side, 1/3 L. And the magnitude of this equivalent point load will be equal to W times L over 2, or the area of a triangle, width times height divided by 2. And so now this problem looks a lot like our previous example above it. And so we can use those formulas here. So our RY1 will be equal to, note that RY1 is now the further distance away from our point load, and so it will be the smaller reaction. So it will be the P times A over L. And we can substitute, now that we know P and A, in different terms for this problem. P is now W times L over 2. A is now L over 3, and the whole thing gets divided by L. So now, solving the algebra here, one of these L's will cancel out, and we will be left with W times L over 6 for our RY1. Now RY2 will be equal to P times the other length, B, the longer length, over L. P is, of course, W times L over 2. B is 2/3 times L. And the whole thing gets divided by L. And we end up with WL over 3 is equal to RY2. Lastly, let's look at these examples which have fixed conditions at either end. Now, in addition to drawing a vertical reaction and a horizontal reaction, we also draw a moment reaction. And so, when we sum our forces in the y direction, we have RY1 minus P equals 0, and we can very quickly solve for RY1 is equal to P. Lastly, for this example, let's solve for our moment reaction mz. So we'll take our sum of moments about the z-axis at the same location as before, at our support, and that will be equal to our reaction moment mz, which has been drawn in the counterclockwise direction, and so it will be positive. And then we will have our moment due to our applied force, which is creating a clockwise moment about our point here. So minus P times the perpendicular distance to our point, L, is equal to 0. And so that gives us that our reaction mz is equal to P times L. I didn't really give myself much room here, but mz equals P times L. Now our final problem. As before with our distributed load, we will start by making an equivalent point load at the centroid of the distributed load. And so that equivalent point load will be equal to the distributed load times the length. Now we sum forces in the y. Ry1 minus W times L equals 0 gives us Ry1 equals W times L for our reaction in the y. As for our moment reaction, sum of moment in the z. Again, mz, our reaction, is positive here. And the moment due to our applied load will be negative w times L multiplied by its perpendicular distance to our support, where we are taking our moment, times L over 2 equals 0. And that gives us mz equal to WL squared over 2. Squared over 2. So now we have a few equations for reactions given various loading conditions. In the next video, we will use these formulas we've derived to draw shear and moment diagrams.